All right. Yeah, it is 5% battery. I forgot my charger. That's right. No, I found it. I just had to run to my office. Yeah. Thank you. All right. So we're broadcasting. I think this is probably everyone who's going to show up. That's okay. There's no quiz. But we are going to introduce project 2. And then after that, we'll do a little bit of other material as well, depending on the time. So project 2 is Gomoku, or 5 in a row, the AI for it. So I'll just briefly talk about AI for board games in general. So, in 96, the Blue lost to Kasparov. In 97, it won. 20 years later, AlphaGo won against Lee Sedol, so one of the strongest Go players, but it took 20 years for Go AI to work better. I have theories about why, but it's not exactly clear. I'll get into that in a second. So how does AI work for board games? So basically, there are two components. So there is the evaluation function. So that's a function that takes a position and outputs some kind of score that corresponds to how well the opponents are doing. How many people play chess or Go or anything? So most people. So like if you play like chess on chess.com, it'll like tell you how well you're doing. It'll tell you the score. It's a number that corresponds to how well you're doing, a little bit like an Einstein midterm. All right. So the other thing that's happening in Chat AI, although less so in the last couple of years, is what's called search. So that is enumerating all the possible ways in which the game could go and saying, if the game goes that way, that will be my score. And if it goes that way, then that will be my score. And then your goal is to make a move in such a way that many turns down the road, the evaluation score is going to tell you you're doing well. Oh. So you've made something that's like an evaluation function for tic-tac-toe in the lab, right? So I'm referring to the is-when function. In what way is it an evaluation function? Well, it will tell you if no one is winning, and then the score is 0. It can tell you if you won, and then your score is 1. And it tell you if you've lost, and then your score is -1. Guys, a little bit too much chatter here. Yeah. All right. Does that make sense to everyone? How the is-when function from the lab is kind of like an evaluation function? Okay. So search would look something like this. So this is just like a comic from XKCD. You'd have to follow the link in order to really see it. I'll just open it in my browser as well. So that's the basic idea for search. I think like you've all now played tic-tac-toe because I made you. So you kind of probably see it, right? So here it kind of maps out all the possible moves. So the red is what you should do. And then if you're playing for the X's, then you just look at what the move was by the knot. So was it this or this or this or this or this and so on. And then the red is saying what you should do next. So the red is the optimal move, the move that's most likely in some sense to lead to a win. Of course, in tic-tac-toe, if you and the opponent are playing optimally, it's a draw. And then if someone messed up, then, well, it's predetermined. Of course, that's the same in chess and Go as well. It's just that in chess and Go, we don't know what's going to happen at the end of the game, which is why we need to rely on an evaluation function that tells you how well you're doing, as opposed to something like tic-tac-toe, where you can just call the is-when function from the lab, and it's going to tell you what's going on. Like either play more and see what's going to happen, or we know exactly what happened. Does that make sense? Questions? Okay. So that's tic-tac-toe. Let's think a little bit more deeply about evaluation functions, because that's going to come up in project 2. So in chess, if you know, like if you've been taught even a little bit how to play chess, they kind of teach you an evaluation function, right? So they tell you count up the pieces and assign, for example, like the systems vary, but 1 point for each pawn, and then 3 points more or less for bishops and knights, and then 5 for rooks, 8 for queens, something like that. How many for king? You really don't want to have a king because it's not a useful piece. You can just lose with it, right? You can get more sophisticated than that, but actually this system already works pretty well. And I think that's why Deep Blue could win against a human much sooner than AlphaGo could win against a human in Go, because in chat, the evaluation function is really straightforward, and the straightforward one works pretty well. You can make better ones, but that already works pretty well. In Go, how many people play Go? So some people. So you, as you know, you can try to count up how many stones you have, and that's going to tell you something, but not very much. It could be that currently you have fewer stones than your opponent and like less territory, whatever, but that doesn't really say much. How would you make an evaluation function for tic-tac-toe? Let's say that you couldn't just look ahead and know exactly whether you're winning or losing. What would you do? Anyone? Yeah. Yeah. No. So like, let's say you can't go, you can't count ahead, right? So I have a position, I have some cross and some X's and some knots there, and I want to know based on where they are, how well am I doing? Adam, yeah.
Number of consecutive like pieces, so like X's next to each other or O's next to each other.
Yeah. So if you have 2 X's in a, if you're playing for X and you have 2 X's in a row, then, well, if your opponent doesn't block you, then you can win next time. So that's good. If you have 2 sequences of 2 in a row, that's great because your opponent cannot block you. Does that make sense? Question? Okay. So that's something that you can do. So the modern evaluation functions, so something like AlphaGo, the thing that won at Go, something like AlphaGo is now also available for chess and plays quite well. They use machine learning rather than something that's hand engineered in order to evaluate how good the position is. Especially in Go, that's really important because in Go, the way people play is they look at the board and they get a sense, essentially, of how well they're doing. It's not, there are textbooks, of course, but there's not really a good way to explicitly say what it means for a Go position to be promising or not. It's just that somehow people learn from playing and get an intuition for how well they're doing. And as it turns out, that's an empirical fact. Computers do that as well. So machine learning works much better than explicitly coding in rules about how well you're doing. So we'll talk about it maybe a little bit more in the 3rd year. But that's kind of an amazing thing is that, you know, for some things like, you know, object detection as well, like if I'm looking at you and I see a face, it's very difficult to exactly say in code what it means for pixels to represent the face. In the same way, it's hard to say in code what it means for a Go position to be promising or not. As it turns out, that's an empirical fact. So for chess, that now works as well. So this is not in the material, it's not in the slides, but the empirical facts are like this. So in chess, it's still the case that you want to search more in order to play really well. So if you want something that's superhuman, you want search plus evaluation. If you just want to like get the equivalent of a human intuition and just play like that, that plays pretty well. So about if you know about FIDE ratings, so about 2400 is what you can get that way. In Go, you can be superhuman by just getting an intuition. So by just using the evaluation without looking any more forward than by one step. Yes.
Some chess engines are better than others.
Yeah.
What is the difference?
Some students are better than others. What's the difference? So one difference is how far ahead you look. And like when you're using a chess engine, you can just tell it like, I want you to play with this strength, and depending on that, it'll just take more time if it wants to play more strongly. Some, like the and there's kind of sophisticated search that makes things faster. Also, if you set up the machine learning a little bit better, it'll evaluate positions more precisely. So yeah. All right. So again, search, that would be enumerating all the possible ways in which the game can develop. And there's many sophisticated methods, which we're not going to talk about, but you can look up. So, all right, this all gets me to project 2, which is AI for the game of Gomoku, or 5 in a row. So that is a game that's like tic-tac-toe, except you need to get 5 pieces in a row, and you're playing on a 15 by 15 board. So traditionally, it's played on like a Go-like board. So for that reason, the pieces are called stones, and there's black stones and white stones, as opposed to knots and crosses, but it's the same principle. Okay. So how would you make an evaluation function for Gomoku? So we've discussed tic-tac-toe. It's kind of similar. And this is from the handout for project 2. It might give you some ideas. So ideas? So I have as an input a list of lists that's white and black. Obviously, those are not real positions because it can only account for white and black and only differ by 1. But that, yeah.
Do we have like a matrix essentially which starts off with just like 0, 0, like it's like a matrix like a 15 by 15?
Yeah, it's exactly like Lab, whatever.
And then we just set it to 1, and then like the second player can set like 2.
Yeah, so like the way I do it is the same way as Lab 6, where I set it to either like W in quotes or B in quotes, but you can do it any way you want. Yeah, not in a project where you need to do it my way. Yeah. Ideas for an evaluation function. Like if you are trying to, granted that maybe you haven't heard about the game before, but if you're trying to tell someone how to win at this game, what would you say? Like, what should they try for? That's the same question, right? Anyone? Yeah. Yeah. So how many sequences? So one thing that I will point out is that in figure 4, it's 3 in a row, but that's useless because you can't extend it to 5, right? And if you look at figure 2, that's pretty good, but it would be better if the white wasn't blocking the sequence of black, because then you could extend it to a 4 in either direction, which means that you can threaten the opponent. Does that make sense? So one way to do an evaluation function is just count up exactly what you said. So count up how many open sequences. So by open, I mean, so something like figure 1, where it's not blocked from either direction. And count up how many semi-open sequences you have. So semi-open would be blocked from one direction, but not the other direction, like figure 2. And then you have all those counts. And the intuition is if you have an open sequence of 4 and your opponent doesn't win the next move, then that means that you won because They can try to block you from one side, but you'll extend from the other. If you have two semi-open sequences of 4, it's the same unless it's like a weird configuration, right? Because they can try to block one semi-open sequence, but you still have the other one. So what I did is just say, okay, if we can count up all the kinds of sequences for myself and for the opponent, then I can assign a score where I weight an open sequence of 4 a lot, and I weight a semi-open sequence of 4 a little bit less, actually quite a bit less, and I weight the open sequences of 3 a little bit, about the same actually, and so on. Does that make sense? So then search is not something that we can do yet with the tools that we have. So what we do is exactly what we did in lab 6. We search by one move ahead. So what you had done in lab 6 is you can have tried to place the piece in every possible square and call is win, right? Exactly the same thing. So we try to place the piece in every possible empty square, and then we get the evaluation function, and we get the move that maximizes the evaluation function. Does that make sense? That's it. That's the project. So let's look a little bit at the code. Oops. That's a shame. Okay, that works. Okay, I'll fix it after the lecture. It's gomoku.py. All right. So the score is given to you. So the score is saying count up the open black, open white, semi-open black, semi-open white sequences, store them in dictionaries. And then I just made this up. So I made this up so that it kind of works pretty well. Actually, like if you try to play against it, it's pretty good. So like if you're not paying attention, you're probably not going to win. Those are somewhat arbitrary. They're just tuned manually, not with machine learning, to play like reasonably well. And what we're doing is we're just saying, you know, we are playing for black. So black in Gomoku starts. And we're saying if there is an open sequence of white of size 4, then that's minus 10,000 a piece, because that means that I'm about to lose. Because the idea here is I just placed the black piece and I haven't won. I'm trying to see how I'm doing. If I just place the black stone on the board and there is an open sequence of white of length 4 or semi-open, I'm done. Right? On the other hand, you know, like if I have an open sequence of black of length 4, then I'm doing great. And then semi-open is pretty good, but not nearly as good because I'm just going to get blocked, and so on. Make sense? Questions about this? Yeah. Because I just placed the black piece and I haven't won. So that means that if there is a sequence of 4 that's not close, then I'm done. The opponent is about to win. Why is like it really doesn't matter, right? So the situation here is I've made the move, so it's like in lab 6. I'm trying to tentatively place the stone on the board. So I've placed the stone on the board and I haven't won. That means that if I'm leaving an open sequence of 4 for white, or an open or a semi-open, then I'm done. It doesn't matter whether it's open or semi-open. Right? Does that make sense? Yeah. So, all right. So that is given to you. And then print board is kind of annoying. So that's also given to you. And then your job is to essentially write detect rows. So detect rows would be a function that takes in the board, and you're saying whether you are analyzing for black or white, and you're saying for what length you're analyzing, and it returns how many open, how many semi-open. Make sense? And then you are also implementing is when. Of course, if you have detect rows, is when is almost the same, right? Because you just need to basically see how many sequences of 5 you have. If there's more than one, then that indicates a win. And then you also have search max. So search max would be like the function from lab 6, where you're trying to place the stone on every possible empty square, and you are returning the move that maximizes the evaluation function. Make sense? Questions? All right. So that is essentially it. So one thing I will note is that I am asking you for is bounded, and that's going to be graded. So is bounded basically takes in the board. It takes in the end of the sequence that you're looking for. So the y coordinate and the x coordinate of that. And it takes the direction. So dy would be like, are you going essentially down, or are you not going down? So dy is either 1 or 0. And then dx would be, are you going right or are you going left? Because you could be going down along the y and left along the x. That would be the diagonal that goes this way.
So it's essentially just like the coordinate system like mapping.
Yes. Yeah. So this is the direction of the sequence. Okay. And then is bounded is supposed to return whether the sequence that ends at the coordinate y and x end, that's of this length, that goes in direction dy dx, is it open or semi-open or closed? And that's one way to do it. It's not the most efficient way to implement detect rows. It's just that I'm trying to build up to detect rows. So I'm making you do it my way, which is inefficient, but maybe a little bit more intuitive than the most optimal thing. All right. Questions about this? All right. How's Discord doing, by the way? Wait, are we not broadcasting? Wait, are we broadcasting? Yeah, I think we are. Yeah. Yeah, we are. Yeah. Okay. Wait, sorry, let me just quickly check.
Here's live, it said live.
Okay, yeah, okay, thank you. So, okay, all right. So hello. Okay. So this is that. So what I want to do now is start new material that's kind of difficult. And I thought about whether to do it or not. And then I thought, well, maybe people want to think it over reading break. So we'll start. So it's about how variables are stored in memory in Python. So what I'm going to do is I'm going to create a table. If you are writing things on paper, how many people are writing things on paper actually? Not very many. Okay, make a table with me. So memory is like a table. Like so, where each address is a cell in the table. So it might go like this. So it might be that you're starting with 1032, and then you go to 1064, and then you go to 1096, and then you go to whatever 1096 plus 32 is, and so on. So 1096 plus 32, 120, 120. Okay. So if what you're doing is saying x is equal to 5 in Python, what happens is, let me just, so that we're technically not incorrect, let's say 500. So what Python will do is it will place the 500 in the memory table. So maybe somewhere here. And then it will keep track of the fact that x refers to the thing that's stored in 1064. So that means that there is another table that's internal to Python, making another table here. And this table that's internal to Python is going to say x refers to address 1064. So I'm writing it down like this because I'm going to try to consistently say, when I'm talking about addresses, I'm going to have the @ sign there. That is just notation. It's really that Python internally says x is whatever value is stored in the memory table at address 1064. I should say at this point that 500 is, of course, arbitrary. The numbers here are kind of made up. It's just that it's a table with addresses. So by addresses, we just mean, the same as street addresses, right? So you have, 40 St. George's Ban, and then, whatever, like 50 St. George or something like that is empty, and so on, right? There is a reason that it's, that I'm writing things down like that, but we'll get into the reason really deeply only in 190. For now, those addresses, kind of like street addresses, are a little bit arbitrary, right? So like sometimes on some streets you skip a lot, sometimes not. Okay. So that is how an integer is stored. If you've taken other classes before in languages other than Python, that might seem extremely weird. Like, why wouldn't you just say x is 500? And the reason is, well, you could do it the other way, but that's not how Python does it. So one way to explain it is that if you are doing something like a string, then with integers as well, of course, in Python, because they have an unlimited amount of digits, but with strings, it's very clear that you cannot just say, well, like it's a string, I'll just store it in one of the cells in the memory table, because some strings can be very large. They wouldn't fit at 1032, for example, because at 1064, we already have 500 that lives there. Make sense? So, okay. So how would that work? So for high, we'll say, okay, we'll pick a place for it. So maybe here. And we'll put high here. So technically, we're not doing this kind of in detail right now, but technically high starts at address 1096, and then it might be that there is a lot of characters there, so it goes up until whatever, 1027, or it could be that it goes up until 2000, if it's a lot of characters. And then we'll say in the variable table, so this is usually referred to as the variable table, we'll say S is whatever is stored at the address 1096. Make sense?
So are these numbers just like randomly?
Yeah, I made them up, yes. This entire thing is made up, yeah. Okay, yeah, that. Yeah. Yeah. So it would, so the way I'm writing it is I'm saying high here, but really it's like H is at 1096 and then I is at 1097 and so on, right? And then if it's very long, it just means that I'm not going to be able to store anything at 1028. I'm going to have to wait until like 1060 in order to do anything. The variable table just says where it starts, and then in the memory table internally, it also has a way of saying how long is it taking, how many spaces. Yeah.
Like, if there was something at like, let's say 1028 already, and then we were like putting the string in, would the computer know like, oh, this string is so long that we can't fit it in between, like?
Yeah, so the question is, if I'm placing a new thing, can it figure out where to place it so that I don't overwrite previous things? And the answer is yes, like it knows. Yeah.
I know you pick up the numbers for the addresses, but in real, like in how it works, are the numbers continuous or like are they just totally like?
Yeah, so the question was, actually, are the numbers continuous? Or so like, is it like 1032, 1033, and so on? The answer is no. So usually they would be like this, where they skip in regular intervals. And the reason is basically that's more efficient in the hardware that way. Yeah. All right. Other questions? But the exact interval would vary, and in principle, you could imagine not aligning them like that, but in modern hardware, they are kind of aligned in regular intervals. Yeah.
Is there a limit to how many, like, how big the numbers can get?
Yeah, that's a great question. So the question was, is there a limit to how many, how large the addresses can be? And the answer is yes, totally. And actually, every time you download software, when you choose 32-bit or 64-bit, you know, how like you sometimes need to choose, that refers to exactly how large the largest possible memory it can be. So is it 10 to the power of 32, sorry, to the power of 32, or 2 to the power of 64? We're not going to get into it until 190, but yes, like the answer to your question is yes. And kind of 32-bit or 64-bit actually determines that. Yeah. Yeah.
Well, that's 1028 should be like 1128.
Say it?
It's
Did I? Oh, sorry.
because that's based on.
Yeah. Thank you. Yeah. All right. Other questions? All right. But they are kind of arbitrary. Yeah, so thank you though. All right. So, okay. So now what I want to do is say, and this is kind of the complicated part. I want to tell you what happens when you say S is equal to X. So in Python, what this means is move this thing here. So take 1064 and copy it over here. Okay. So take 1064 and copy it over here. Now, in practice, what does this mean? All it means is now that they said, you know, assign X to S, like when I'm saying S and when I'm saying X down the road, it's going to be 1064 both times. So 1064 would be 500, right? So print X, like print S, will print 500. So in a way, this is nothing new. But under the hood, what's going on is that now S and X both refer to cell 1064. Yeah. Why is it sorry, because I'm messing things up. It used to be 1096 and now it's 1064. Thank you. Yeah.
Modify the value of X and S, but S also gets modified?
So the answer to that question, think back. So I want to throw it back at you. So remember what we were talking about on Wednesday? with mutable and immutable objects. So integers and strings in Python are immutable. There's no changing the contents of S and X.
Redefine X.
So redefining is this, right? Redefining is saying, take a new right-hand side and put it in the left-hand side. So there is such a thing as modifying the contents, just not with strings and integers. And we're about to do that. Make sense? So, okay. So, so far I haven't told, so your question was actually excellent. So far I haven't told you anything that's interesting. Because you didn't have to know that under the hood, what's happening is the 1064 gets copied rather than the 500. Doesn't matter. Either way, print of X and print of X produce the same thing. So, so 500, right? But to your question, if it's lists, then it really matters. So if I'm defining a list, and let's say that the list is X and S, and let's say that this is commented out, so that this is, luckily on YouTube, you can play things back, so that this is high, so 1096. So what does L equals XS do? So it creates a list, and that means that it puts this in the memory table. So the way I'll write it is, so X is 1064, and S the at thing is labeling like people I know. Well, all right. I do not have compromising, acquaintances. So and at sorry, and S is at 1096. And now that that's created, we can say that L is at 2028. Is that making sense? Questions about this? Yeah. 100. Oh, I just made it up. Yeah. All right. Yeah.
If we change S back to 1096.
I mean, because I commented out. Oh, okay. I commented this. Oh, why is it not letting me comment things out? This was commented out. Oh, I think it thought it meant something else. Okay. Are we all right with all of this? So to recap, we said X equals to 500. We placed 500 in cell 1064. And we said X refers to 1064. We said S is equal to high. We placed high in 1096. And we said S refers to 1096. And then we made the list X comma S. And that means that, this is at 1064, this is at 1096, and the list L lives at 2028. Are you with me so far? Who's not with me? 9 minutes before 5, so probably some people. All right. So, okay, so now back to you. Oh, you have a question.
Would it create?
Yes. The answer is yes, and I'm just trying to wrap the story up by 5 o'clock. And for that reason, I was trying to be technically correct here, but yes, you're exactly right. It would first place them in memory. All right, yes.
That's not a list of assigned to it, it's just itself a list of investment.
Yes,
It contains a list of investment.
yes,
That list of addresses is itself assigned to an investment.
yes. So what you said is the list is actually like a bunch of addresses, and this bunch of addresses itself has an address. Yes, that is all correct. All right. Other questions? All right. So now to your question. So what happens if we say something like L at 0, so is equal to, let's say, S, right? So you know what it's going to be. So L is high, right? So that's not a question. But what happens here is that we are changing this guy, right? So this guy used to be 1064, and now it's going to be 1096. All right. So, okay, that's not super interesting. But here's the interesting part. Let's say that in between, we said L1 is equal to L. So what happens is that anytime you have an assignment where you're just assigning the right-hand side, which is a variable, to the left-hand side, which is a variable, is you're just operating on the variable table. So that is just going to say, I have a list L1, and I'm just copying this over here. Make sense? Yeah.
So the length of whatever is being stored within the variable, would that also influence the length of like the address?
Yeah, so the length of the address in the sense of the number of digits, or so, I mean, technically, yes, in the sense that if the thing is very large and contiguous, then you would have to find an address somewhere where there is space, and probably that's going to have more digits. But that's just kind of the notation. Again, kind of the actual address has a fixed length, like it just like has zeros on the left. Yeah.
Does it correspond with like the number of bytes? Like if they're foreign numbers in the address, right?
No, so the answer is like addresses are fixed length. So they have a fixed number of digits. So either 32 bits or 64 bits, whatever it is. Okay. Yeah. That was kind of an answer to your question. We haven't covered that.
Okay.
Okay. All right. So back to here. So, and this is like not easy stuff. We're going to go over it several times. So if you're saying L1 is equal to L, what happens is Python kept track of where L is, and now it's, sorry, just give me 3 more minutes. Guys, blue short, orange short, hello. 3 more minutes, 4. All right. So what we're doing is we're saying, when we're saying L1 is equal to L, we're taking this and we're copying it over here. So why does that matter? That matters a lot, because when we're saying L at 0 is equal to S, not only does L become high, but L1 as well. And if you don't believe me, we can check. So let's say that you say L is 5, 6, 7, and then you say L1 is equal to L, and then you say L1 at 0 is equal to 42, and then we print L and L1. They are the same. So this phenomenon is, so this is kind of like this kind of a weird action at the distance kind of thing. If you know, like in physics, there is like no action at the distance, or according to some people, in programming, not so much. So this is referred to as aliasing. So two variables referring to the same address in the memory table. So alias in English is like, alias means another name. So like an assumed name or something like that is called an alias. All right. So it's a thing. If you don't know about it, obviously your code will have bugs. So that's why we're doing it. It's not easy. We'll do more of it after we come back. Enjoy reading break. If you're coming to dinner dance, I'll be happy to take a picture with you, with my jacket. And I will see you in about 9 days. See ya.